Hello students, welcome to the first lecture of your course Thermodynamics. In this lecture I will give you the brief introduction of thermodynamics. The name thermodynamics, which came from two Greek words, the therm, which means heat, and the dynamics, which means the power. And this is the early effort to describe thermodynamics, where it deals with the conversion of heat into power. However, in today's time, the thermodynamics used in many aspects, which includes different aspects of energy transformation, including power generation, refrigeration, and the relationship among the properties of matter. We can define thermodynamics in different way. However, I have shown you two ways you can define a thermodynamics. One way, we can define thermodynamics as a axiomatic science, because it's based on axioms, it's based on some laws, the laws of nature, it's based on some laws of nature, where it deals with the relations among the heat, work, and properties of the system which are in equilibrium state. So, and it describes the state and the changes in state of physical system. And we can also, other way also, we can define thermodynamics is the science that deals with the interaction between energy and the material system. So whatever the laws it's based on, we can have four laws in thermodynamics, and it starts with the zeroth law of thermodynamics. Then we have first, second, and third law of thermodynamics. However, the zeroth law of thermodynamics, it is developed after the first law of thermodynamics, but whatever the zeroth law signifies, it has to precede the first and second law of thermodynamics. That's the names has given like this. So what is the purpose of the zeroth law? The zeroth law gives the concept of temperature. So it deals with the thermal equilibrium, concept of thermal equilibrium. However, the first law is the law of conservation of energy. So it shows that energy is a thermodynamic property, and it gives the quantity over energy, thermodynamics. However, to know the quality of energy, we need another law. That law is known as the second law of thermodynamics. So second law of thermodynamics gives the energy, asserts that energy has both quality as well as quantity. The first law doesn't give the direction in which direction the energy conversion will be takes place. So energy in transition, we can see in later in subsequent classes that energy in transition, heat or work can be done either heat or work. So which direction energy conversion or heat transfer going to take place, that is given by the second law of thermodynamics. It shows that if the energy actual process, whichever actual thermodynamic process, can only occur in the direction of decreasing quality of energy, that so decreasing quality of energy, that is like it is the increase in entropy. Similarly, we have after that, with that, these things we will going to discuss in subsequent classes, where this we have mostly deals with each of the law. Then we got the third law. However, the third law is excluded, is not discussed in your syllabus here. So it is excluded from this syllabus. However, you just know the definition. What is states that the third law says that entropy of a system approaches a constant value as its temperature approaches a absolute zero. And so these are the four laws of thermodynamics. So however, we can study thermodynamics based on two different approaches. In case of, even if you see in fluid mechanics, in all the whatever the mechanics, if you're going to something related to mechanics, or if you're going to study, they study either in macroscopic, based on the macroscopic approach. That is, macroscopic means whatever the properties are there, whatever the variables where all are macroscopic, these are measurable quantities. And other way also we can study mechanics is a macroscopic approach, which is microscopics, which is molecules of a system, molecules. So here the macroscopic approach, that is falls under the category of classical thermodynamics. So it is based on the continuum idealization. So what do you mean by continuum? That the properties of the system are continually varying in the space. So whatever the properties are signifies the system are the function of the space variables. So they are the what we can define at any space. We can define any properties. So these are continuously varying. There is no discrete. There is no gap in between them. So there is no jump discontinuities are there. However, this idealization is valid if the Nansen number is very low. So what is the Nansen number? The Nansen number is the ratio of the mean free path of the molecules then the characteristics length of the system. Whatever the system, what is the flow configuration you have taken, whatever the system you have taken, is characteristic length of the system. So mean path variables, that is, we can also if you want to know, the mean path variable is the average distance traveled by the molecules for while making a collision to another molecule, making collide with the another molecule. So if the Nansen number is very less, that is that system size is characteristic size of the system is very high, then the continuous this assumption is valid. So in that case we take the macroscopic properties. So and other also is describe the states of the thermodynamic system at near equilibrium, and those both are using the macroscopic or measurable properties. The values or properties are the average values. That is the, if you say the pressure is a measurable macroscopic quantity, which is the average value of the pressure exerted by those macroscopic individual molecules, millions of individual molecules that is contained in the system. Because of the pressure exerted by those individual molecules, we got the pressure what is measurable in the macroscopic approach. So in this approach, certain quantities matter is considered without taking into account. We are not concentrating on the what is what is going inside the molecule, what going inside them in the macroscopic level. We are not concentrating. We are only seeing the whatever the outcome of this thing, what is the average of this thing. So it is also used to model exchange of energy, work, heat based on the laws of thermodynamics. The second one is the macroscopic approach. Here the Nansen number is very large. So mean free path or Nansen number is greater than equal to 1. So mean free path or the system size, the characteristic size of the system is equivalent. So we can take individual molecule. We can concentrate on individual molecules. So that is approach is the macroscopic approach. So this is made up. We know that the system is made up of very large number of discrete particles, which are molecules. So it is the based on the. But however, with using the statistical thermodynamics, we are doing that. We are taking the not taking the individual molecule. We are taking the average of this whatever the behavior. We take some group of molecules and we take the average of that the behavior of that group of molecules. And this is using some statistical methods. And this process is very very complicated because you have to deal with large number of molecules. So normally in this course, whatever is we're going to use, that is based on the macroscopic approach. So as we have seen that if you look around yourself, you'll see the application of thermodynamics in everywhere. So inside ourselves, our human body is experiencing heat, so that is also falls under thermodynamics. Then we have the other practical applications like air conditionings, aeroplanes, wherever you have seen car radiators, power plants, refrigerators, all are where we have seen is that there is some thermodynamics is going on. So these are some of the applications which I have shown here using some figures. So this way I have concluded your first class. Thank you.